Hi, my name is Young, and today I want to talk about design, fabrication, and characterization of miniaturized lensless fluorescence imaging device. Fluorescence microscopy is a powerful tool in biomedical research. In its simplest form, excitation light is directed through an objective lens onto the sample, stimulating fluorophores to excite longer wavelength light that then can be detected. As you can see here, the conventional fluorescence microscopes are often large and bulky. This creates a significant limitation for application where miniaturized imaging platform is desired. Lensless imaging has emerged as a compelling alternative for a traditional lens-based system. It offers a compact, lightweight, computationally driven approach that eliminates bulky optics with resolution comparable to conventional microscopes, as you can see here. This is particularly attractive for a portable and wearable biosensing platform where space is a limitation. Unlike conventional imaging system that uses lens to focus light and form direct image, where each pixel corresponds to a specific point in object space, lensless imaging takes an indirect computational approach, an optical encoding element that is placed near the sensor to modulate the incoming light in a known way. Those raw measurements are then processed using computational algorithms to reconstruct the original scene. So how do we go about designing a lensless device? The first step is to design a point function which describes how the system encodes light from the scene onto the sensor. An ideal PSF for lensless imaging should check a few boxes to ensure effective encoding and a robust reconstruction. It should incorporate a directional diversity to capture textures from different angles. It should be spatially sparse to suppress a DC component and have a high contrast to offset the sensor's bit depth limit and include large zero intensity regions. In this work, we use a contour-based PSF derived from Perlin noise, designed to approximate those ideal characteristics while remaining compatible with the fabrication process. Second, we need to determine the working distance, required resolution, and the field of view. Those parameters help narrow down key design specifications, such as the distance from face mask to sensor. Once we have established those parameters, for example, target PSF, the propagation distance, and the wavelength of incident light, we can proceed to design and optimal the face mask. The face mask can then be fabricated using high-precision additive manufacturing process, such as two-photon polymerization. Here is what a prototype looks like. It has an imaging sensor, face mask, and a hybrid optical filter stacks for isolating fluorescence signal. We evaluate the spatial resolution of our lensless imaging prototype using a fluorescence USAF resolution target. We show that the system achieved a resolution of approximately 125 micron at the experimentally determined optimal imaging distance. However, the resolution degraded to 188 microns at design specified working distance of 24 millimeter. Finally, we imaged fluorescence test target that consists of 1 millimeter diameter fluorescence dots arranged in with 1 millimeter spacing in 40 by 30 millimeter grids. From this experiment, we determined the effective field of view of the system to be approximately 27 by 27 millimeters. So in conclusion, we have shown that a compact lensless fluorescence imaging device can achieve large field of view with high resolution while keeping a really small footprint. This sets a stage for future work towards real-time high-quality imaging for biomedical use as we keep improving computational model, hardware acceleration, illumination strategy, and the fabrication process.